Welcome to my channel everyone. Today we will be learning about assembly, more specifically x86 assembly. Now before we dive right in, let's get a few things straight. What is assembly? If you go by the Wikipedia definition, it is any low-level programming language with a very strong correspondence between the instructions in the language and the architecture's machine code instructions. While this definition does sum up assembly pretty well, I would say there's more to assembly than what meets the eye. You see, assembly is the one language which gives you absolute control of the hardware. It's quite a break from traditional programming as we know it. Concepts like variables, structures, classes, unions don't really apply here anymore. It's just you with the machine. You have great power, but of course, with that comes great responsibility. Generally speaking, assembly is the closest you can get to the machine's hardware, apart from directly writing bare instructions with a hex editor. Now, why would you want to learn assembly? This is a pretty valid question one might ask, and honestly, to be fair, there aren't a lot of reasons why. Long gone are those days in the 80s when all software had to be written in assembly because high-level languages simply didn't exist or weren't popular enough in the industry. However, I think personally it is important to learn how our machines work under the hood. You could go your whole life writing code for systems as a part of your job, but can you really call yourself a programmer when you don't know what programming without rules and frameworks looks like? Also, if you're inclined to systems level programming like I am, assembly is your go-to friend for almost all kinds of tasks, whether it be setting up page tables in an operating system or writing device drivers. You need assembly. Also, due to the fine-tuned control that assembly provides you with, learning assembly can give you an edge over others, as you can optimize your code to an extent thought impossible by your peers. Now with the basics out of the way, let's divert our attention to something else. Assembly is deeply tied down to the hardware. In fact, different types of hardware have different types of assembly. In this series, we will be focusing on the x86 line of CPUs and their assembly language specifically. x86 is the computer architecture invented by Intel with the release of the 8086 processor in 1978. In fact, the x86 architecture is still what drives most consumer PCs like yours and mine. Hence, this is the architecture whose assembly we will be focusing on, as it allows you to get up and started with assembly without having to obtain any special hardware specifically for doing what it is shown in the later part of this video. We'll first look at some example assembly code and dissect it step by step, and I will provide additional context whenever necessary. All my explanations shall use the Intel Software Developers Manual, hereon referred to as the SDM, as a reference. You do not need to sit with this book in front of you, but remember, this book is the Bible of x86 assembly, and if you do consider learning assembly in the future, this is your only reference book. So with that, let's dive right in. The code that you see on the screen right now is the classic Hello World in assembly. There are certain OS specific terms and practices that are being used here, which goes on to show that assembly is not only tied to the hardware but also the OS itself. I am using Debian Linux 12 here, but you can use any Linux distribution of your choice. The only important thing to note here is that Microsoft Windows cannot be used for trying out this code, as Windows uses different conventions than those used here. If you use Windows on your computer, you might consider running a Linux virtual machine on your system, or using the Windows subsystem for Linux, WSL that is, to run the code for yourself. Now, getting back to the code, let's zoom in a little bit for some clarity. Right. Let's take a look at line 1. Global underscore start. This line declares a symbol start. What is a symbol, you might ask? A symbol is the generic term used for variables, functions and other similar entities in assembly. In this context, we are defining a function underscore start whose definition we will see in the following lines. So underscore start is a function symbol, that is a symbol that attaches a name to a piece of code. See, now here's where things get interesting. A symbol is just a name for something and a function is just a block of code. You should keep this in mind while we peruse through the rest of the code. Now also about the global part, this actually says that underscore start is declared for all other files to view. That is, it means that the underscore start function is exported to other files. Although underscore start is not generally a function that's linked to by other units, it is still open for other files to use. This does not really make much sense here, but when we try to link this file after assembling it, this part is required because otherwise the linker will not be able to provide an entry point to this executable. A lot of terms are being used here, but I'll clarify them later on. Go to section .text. This line translates to take whatever is next and put it in a section called .text. Now let's break this down. What is a section? We are all used to seeing executable files, the classic .exe on Windows. Executable files are broken down into multiple so-called parts called sections. This is a little bit of an oversimplification, but my point still stands. Each of these sections have a name, a size and some contents. Now by convention, some sections are predefined and are always used for storing a particular kind of content. One of these predefined sections is .text. .text is always used to store executable code for an executable file under Linux. Your operating system may do something differently. Now that we know what a section is and what the .text part means, it's kind of obvious what this line does. We are going to be defining the function underscore start shortly, and this statement asks the assembler to just put the code following it into the .text section, as we are going to define a block of executable code. Next, we see underscore start followed by a colon. This statement is called a label definition. Underscore start is a label defining a name for the piece of code following it. This is very easy to correlate with the real life as well. You can think of this statement as kind of putting a name tag on one's belongings to identify that it belongs to them. If we ever wanted to refer to this piece of code from somewhere else, we would use this name instead of copying the whole thing over, making life a little bit more convenient. A label is in fact the name of a memory address in very crude terms. We'll get into this over again when we discuss section.ro data. Next we have the code itself. Now all the preliminary statements that we have just discussed up to this point only inform the assembler about some things it needs to know, but they themselves do not generate any code. The next line and the ones that follow it will define instructions that will generate actual code. So let's start looking into them now. However, we will need to know a little bit more about how x86 works in order to enhance our understanding of the code. The first thing we need to know are registers. A register is a piece of memory that is present on the CPU chip itself and is quickly accessible to the CPU. Unlike traditional memory, registers don't have an address associated with them. You can think of them as small fixed size boxes which the CPU prefers to have its data in. Note the word prefers. The CPU likes to have all its data in registers, but it may not necessarily be able to have the data there. The registers also have names given to them. In this video, we are using x86 64, that is the 64-bit version of x86, which provides 16 registers, namely RAX, RBX, RCX, RDX, RSI, RDI, RSP, RBP, and R8 to R15. With this in mind, we will look into the remaining ones in the next part of this series. Now, we look at a real instruction. Let's take this instruction bit by bit and try to understand what it's doing. So, mov rax, 1. Frankly, this instruction merely moves a value into the register rax. The word mov stands for move. This is the name of the instruction. Next we see rax and 1. These are the operands to the instruction mov. Operands are basically what the instruction will operate on. It's much like saying 4 plus 3, where the plus is your instruction and 4 and 3 are your operands. The addition operator works on 4 and 3 to produce 7 as an output. Similarly, mov works on rax and 1 to do something. Now, in Intel assembly syntax, the same syntax that you will find all across the SDM, the first operand is the destination and the second one is the source. Intel syntax enforces this rule and you must remember it while writing assembly code. This means that rax is the destination and 1 is the source. Now if you compare these terms to a bus ride, we always travel from the source to the destination after all. Similarly, mov works on the source, that is 1, and moves it to rax, thus completing the bus ride analogy. In summary, the mov instruction is a bus that carries its second operand to the first one's location. After this instruction, the register rax now has the value 1. If you can think of registers like variables in high-level languages, then we have just set the variable rax's value to 1. The next instruction, mov RDI1, does the same thing but for the RDI register. Now with this, we come to the end of this video. This video serves as a primer and as a modest introduction to x86 assembly. The next video will talk about the next few instructions and how they print hello world to the screen. If you like this video, I would really appreciate it if you hit the like button. Feel free to add any feedback in the comments. Until next time.